Welcome to the deep dive. Keeping up with AI research these days, wow, it's relentless. And sometimes those big headlines, those breakthroughs, they need a second look.
They really do.
Today, we're digging into a paper that does exactly that for language model reasoning, especially mathematical reasoning. It turns out some of those big gains might be on, let's say, shakier ground than we thought.
That's right. The paper is a sober look at progress in language model reasoning, pitfalls and paths to reproducibility, Hochler and colleagues. Think of it as kicking the tires, scientifically speaking, on recent claims.
Kicking the tires, I like that.
Yeah, they really look hard at whether these performance boosts are actually reproducible. And, well, what they find is pretty important for us, researchers, engineers.
Right, so our mission today is to really unpack the core findings here. We want to flag the potential pitfalls in how we evaluate these models now and look at the paths they suggest for, well, more reliable assessment. For you, our audience, you're technical, you follow this stuff. This is about getting a clear view, cutting through the hype.
Absolutely.
Yeah.
And for anyone wanting the super quick version, the first minute takeaway is basically this. Recent progress claims in LM reasoning, especially for math, might be too optimistic.
Okay.
The paper shows performance is really sensitive to the evaluation setup. Things like decoding parameters, how you ask for the answer, random seeds, even prompt formatting and the hardware you run it on.
Wow, okay.
And reinforcement learning.
Yeah.
Popular technique, right? But it often gives only modest gains, and sometimes it's just overfitting, good on the test, bad elsewhere. Supervised fine-tuning, though, that seems more consistent, more generalizable.
That's interesting.
Yeah, and the authors push hard for standardized evaluation, and they've actually released their code, which is great for reproducibility.
Excellent. Okay, let's unpack this somber state of LM reasoning for math. That's quite a phrase. One of the big things they found was a pretty significant drop in performance for several recent models, right? These 1.5 billion parameter ones.
That's right, reasoning-enhanced models.
Like DeepScaler 1.5b, OpenRS3 1.5b, 1.5b, FastCarrel 1.5b. They reran them on the A1824 benchmark using their standard framework. Amy is that tough high school math competition.
Yep, American Invitational Mathematics Examination. And yeah, the drops were quite something. You see it right in their first figure.
What kind of numbers are we talking?
Well, DeepScaler 1.5b, down 6.1% from what was originally recorded. OpenRS3 1.5b, that one dropped a huge 17%.
17%.
Yeah. Pyth 1.5b dropped 2.2%.
Yeah.
FastCarrel 1.5b down 6.8%. So even with these smaller models, just changing the evaluation setup causes these big swings.
Yeah.
Makes you really question those single numbers people report, doesn't it?
It really does. And then looking at the same figure, they point out that the improvements some methods claimed, they weren't actually bigger than the natural performance wobble of the base model, DeepSeek R1 1.5b.
Exactly. Just by changing seeds or tweaking settings like top and temperature, you could get that much variation anyway.
Could you quickly remind us what top and temperature do?
Sure. So temperature controls randomness in the output. Higher means more creative, maybe wilder answers. Lower is more focused, deterministic.
Got it.
And top sampling. It makes the model focus on the most likely next words. Lower top means it only considers the very top probability options. Higher top lets it look at a wider range. So you're basically tuning how creative versus conservative the model is.
Okay, that makes sense. So the fact that some new methods didn't improve things more than just fiddling with those knobs on the original model,
Yeah.
that really highlights.
Yeah, really hammers home how crucial multi-seed evaluations are. You need to run it multiple times with different random starting points to get a stable idea of how good the model really is. Otherwise, you might just be reporting statistical noise, especially on these benchmarks we rely on.
So much variability. Okay, the paper sets this up by talking about reasoning as a key frontier for LLMs, large language models. And they mention all these cutting-edge systems coming out, right? OpenAI, OWN, Anthropic, O3, XAI, Meta, DeepMind, all in 2024, 2025. Feels like a gold rush.
It absolutely does. It's just a massive push to make these models better thinkers, better reasoners, new architectures, new training tricks.
Yeah.
Lots of optimism. People think we're close to really powerful reasoning engines.
But, and this is the paper's main point, I guess, the speed creates a risk. We might be forgetting about methodological rigor, how we actually check if we're making progress.
Precisely. That's where the worry about non-reproducible results comes in. If our tests aren't solid, if other labs can't get the same results, then our whole understanding gets skewed. We could end up chasing ghosts, right? Wasting time on things that don't actually work. And it's not the first time this kind of concern has come up in ML. They mentioned that too.
And they focus specifically on math reasoning as the test bed here. Why math?
Well, math reasoning has become super popular for benchmarking LLMs. You've got data sets from Hugging Face H4, AIMO. Lots of people use them to see how well models handle complex quantitative problems. Plus, math problems are often structured, which can make evaluating the reasoning steps and the final answer a bit more objective, you know?
Right, less ambiguity sometimes. Okay, let's dive into the sensitivity issue. The minor details that can throw off performance. You mentioned decoding parameters, prompts, seeds, hardware, software.
Yeah, this is really key. They found math benchmarks are just surprisingly fragile. Like subtle changes in temperature or top, the exact wording of the prompt you give the model, or just running the same evaluation with a different random seed, boom, statistically significant differences in performance.
And Table 1 in the paper shows this, right? How different the setups are across published models.
Exactly. It lays it out clearly, different evaluation frameworks, different sampling parameters. It's all over the place for these open weight reasoning models. No standardization.
They also mention the problem with small benchmarks like AM24 and AMC23 having only 30 or 40 questions. That's not many.
No, it's not. And with so few questions, each one carries huge weight. Get one more right or wrong, and you're past the one score to get it right first try. Jumps by like 3 percentage points or more. So it's just inherently noisy, makes it really hard to trust results from a single run on those benchmarks.
So Section 3 really tries to get to the bottom of why it's so unstable. What are the root causes they identify?
They break it down into a few things. One is just basic sampling variance. The model is probabilistic, so you get different outputs. Then, as we said, the decoding settings, Temp. Also, the evaluation framework itself. Different libraries might use different prompts by default, or parse answers differently.
Okay.
And finally, hardware heterogeneity. Even the specific computer chips you use can introduce small differences that add up.
Right. So given all that, all these ways things can go wrong, what do they suggest we actually do? What are the best practices for reproducibility?
Okay, this is where they get constructive. Their main push is for a standardized evaluation framework. And to show why, they reevaluated a bunch of recent methods using their consistent setup.
And what did that reveal?
Well, one big finding was about reinforcement learning, RL. On these distillation-based models, like DeepSeek R1, it turns out the gains were often statistically insignificant. And worse, it looked like they were prone to overfitting, especially on that small AIM24 benchmark.
So the model just learned the test questions.
Kinda, yeah. It got good at those specific problems, but didn't generalize well. And this contradicts some earlier, more optimistic reports about RL's effectiveness here.
What about OpenRS? That one seemed promising initially.
It did, yeah. But under their standardized reevaluation, those initial gains just didn't hold up consistently. It really shows the danger of relying on results from, maybe less carefully documented setups.
And RL on base models, like Quen 2.5 math, slightly better, but maybe not as good as instruction tuning.
Generally, yes. They found RL on base models did show bigger gains over the raw base model compared to RL on the distilled ones, but often still lag behind standard instruction-tuned versions. OpenReasoner 0 was an exception. They noted it performed well consistently.
Interesting.
But the broader pattern with RL was this concerning drop-off on newer benchmarks like AIM25. Models did well on AIM24, then worse on AIM25. Strong sign of overfitting.
Yeah, that's not what you want. You want general reasoning ability, not just acing one specific test.
Precisely. We need better, tougher, more diverse benchmarks to really test generalization. And contracting with RL, they found supervised fine-tuning, or SFT, that consistently gave stronger, more generalizable improvements across the board. SFT seems just more robust for boosting reasoning based on their analysis.
And putting their money where their mouth is, they release their code, prompts, outputs.
Yeah, everything, which is fantastic for the community. It lets people check their work, build on it. It's proper open science. Really helps move the field forward reliably.
Okay, let's drill down into Section 3 again, the design space of reasoning evaluation. Table 1 showed the mess of different conditions used before.
Right, just highlights the total lack of a standard approach. Different teams using different tools, different settings. Makes comparing Model A from paper X to Model B from paper Y almost meaningless.
Yeah.
Apples and oranges.
So their own setup was super careful. 9 models, 1.5B and 7B params covering different training styles. RL fine-tuned ones like Deep Scaler, OpenRS, and SFT ones like S1.1 OpenThinker.
Yep. And they tested them on AV24, AMC23, and Math 500 using pass at 1 mostly. Crucially, standardized environment. Docker A100 GPUs, AMD CPUs, Lightful with Vellum backend, fixed sampling parameters 2, 10.8, top 0.9, consistent max output lengths, a level playing field.
And first up, seed variance, figure 2. What happened when they ran evaluations with multiple seeds?
It was pretty striking. The standard deviation on pass at 1 scores could be huge, 5 to 15 percentage points, just from changing the random seed running it 20 times.
15 points.
Yeah, especially on those small benchmarks, ANA24 and AMC23. It just screams. Single seed evaluations on these benchmarks. Highly unstable. Don't trust them. 1 or 2 answers different, and the score swings wildly.
So definitely need to average over multiple seeds. And comparing models gets really fuzzy when performance is close and the data sets are small.
Exactly. On AME24, with only 30 questions, each question is over 3% of the score. So tiny random fluctuations can easily change which model looks better if their true abilities are similar.
Did bootstrapping help stabilize the estimates? Figure 3 looked at that.
It did. They showed on AME24 that the variance of the mean pass at 1 score drops sharply once you average over, say, 10 or more seed runs. So bootstrapping over at least 10 runs, especially for small benchmarks, seems essential for getting a reliable performance number.
Okay, then they looked at variance just from temperature and top, figures 4 to 7.
Yeah, and it's interesting how much these knobs matter. Higher temperature could sometimes push peak accuracy higher, but it also made results less stable. A classic trade-off.
Right.
Higher top, on the other hand, generally seemed to help performance without adding much instability. But the main point was that both could cause big swings up to 15% from temperature, 8% from top, especially on small benchmarks. You really need to tune these per model for fair comparisons.
And not just software settings, hardware and frameworks too. Figure 8, table 2.
Yep, often overlooked. They ran the same models on 5 different compute clusters, different GPUs, different memory. Performance on AME24 varied by up to 8% for one model, 6% for another, just based on the hardware. Even using standardized inference engines like VLLM, which try to optimize for hardware, these differences pop up. And comparing 2 evaluation libraries, Light Velvel versus Alchemy, showed 1 to 2 percentage point differences sometimes. The message is clear. Even if you think you have the same setup, subtle differences in hardware or the software stack can change the result.
Okay, finally in that section, prompt format and context length. Figures 9, 10, table 5. How important are those?
Very important, especially context length. If you cut off the model's output too soon, low max new tokens, performance tanks, especially for problems needing long reasoning chains.
Makes sense.
And prompt format matters too. Models did best with math-specific prompts that use their native chat template the way they expect to be talked to. If you just gave them the raw problem without the usual chat structure, especially for instruction-tuned models, performance dropped. So yeah, give them enough room to talk to them in the way they expect.
Okay, so after laying out all these problems, section 4 proposes the way forward. Standardization. What are the key recommendations?
They get pretty concrete. Standardize the hardware-software stack. They suggest Docker, maybe using something like RunPod for consistency. Report variance. Use at least 10 seeds for small benchmarks. Report mean and standard deviation.
Essential.
Optimize hyperparameters like temp top per model, then fix them for evaluation. Use appropriate context lengths and the correct chat templates. Use robust answer matching, not just exact string match, maybe something latex-aware like LightDevel uses.
That seems smarter for math.
And finally, be transparent. Release everything. Code, prompts, outputs, document your whole stack, report uncertainties, do qualitative analysis too.
And they actually did this themselves, right? Their standardized procedure.
They did. Consistent setup, RunPod A100s, evaluated models from Table 3 across 6 benchmarks, including the newer AIM-25 Minerva Olympiad bench. Use LightDeal with VLLM, 10 seeds for AME-MC, 3 for others. Use model-specific settings like max tokens, optimal hyperparameters, correct chat templates, and that latex answer extraction.
So the sober look results. Table 3. What did the standardized comparison show?
Okay, so for RL on that R1 distill base, mostly no significant gains over the baseline. And DeepScaler was the main exception. RL on base models like QuenMath, some gains, but generally less effective than instruction tuning. OpenReasoner 07B was again a standout RL model, though.
And the overfitting.
Yeah, clear trend for many RL models. Performance dropped from AIM-24 to AIM-25, but the supervised fine-tuned models, they consistently beat instruct-tuned baselines and generalized better to AIM-25. SFT just looked more solid. Though they noted one SFT model, OpenThinker 2, did show some degradation, maybe suggesting overfitting from how its data was curated.
So RL seems tricky, prone to overfitting here, while SFT is delivering more reliable, generalizable progress right now. Did they also look at things like whether wrong answers are longer? Or diversity collapse?
They did. On response length, figure 11, appendix fix, yes, consistently incorrect answers tend to be longer than correct ones. Across models, across data sets. More pronounced for RL models, but true for SFT too. Might be a useful heuristic, actually.
Interesting. And diversity collapse, the idea that training narrows down reasoning paths.
They looked at pass at K as the right answer in the top K outputs. Table 4. They didn't find consistent evidence for diversity collapse with RL. Usually when pass at 1 went up, pass at K went up too. Suggests the models aren't just learning one single path. Standard decoding seems okay at finding diverse good answers.
Okay, so wrapping up then, section 5. What's the final verdict from this sober look?
The big takeaway is that a lot of the claimed progress in LM reasoning, especially math, rests on unstable foundations. These minor evaluation differences cause major performance shifts.
Right.
RL, while promising in theory, has shown modest gains in practice here and seems really prone to overfitting specific benchmarks. SFT, however, seems to deliver more consistent, generalizable improvements.
So the call to action is?
It's a strong call for standardized, transparent evaluation protocols. We need to shift focus from just climbing leaderboards to ensuring our methods are rigorous and our results are reproducible and actually mean something.
Okay, so quick recap for you listening. This deep dive really highlighted the fragility of current reasoning benchmarks. Some popular methods like RL might not be the silver bullet we thought, showing overfitting issues. Supervised fine-tuning looks more reliable right now. The core message: we desperately need more rigor and transparency in how we evaluate these powerful AI systems.
Yeah, and it leaves us with some big questions, doesn't it? How should we interpret future results now? Should the community really prioritize robustness and reproducibility over just hitting soda on potentially flawed benchmarks?
Good question.
And what new ways do we need to really measure general reasoning ability beyond these specific tests?
Definitely things to think about. We really encourage you to check out the paper itself, links in the description, and the code they released. Try running things yourself. Contribute to better benchmarks. We need that collective effort. Join the discussion. Your insights matter. Thanks for taking this deep dive with us today.